Okay, here we go. We got a couple questions off of 9.2. I already started writing up what number 3 is before I got distracted. So we have this chemical reaction. We've got 2A plus B goes to 3D. It's asking us to rewrite the rate of reaction in terms of the differential form for each component. And then it also wants us to figure out, if we have this known rate associated with A, what is the rate of B and D? And I should, at this point, this would actually be just a delta A, delta T. That's our rate. Right, this is the rate with respect to component A, not the rate of reaction. And this is, again, one of those places where our attention to key terms and vocabulary becomes really important. So if we looked at the rate of reaction, right, compound A is going to be disappearing every time the reaction takes a step, right? As the reaction proceeds, compound A is going to be disappearing. And it's going to be disappearing twice as fast as the reaction is going, because it's 2A per reaction. That means if I wanted to write down the rate of reaction, my rate of reaction would be, and I'm writing it relative to how compound A is changing. Right, compound A is changing twice as fast as the reaction is. So I need a factor of 1/2 in order to get it so the rate of half of A is equal to the rate of reaction. And then I also need to take into account that this delta A is going to be negative because this is a reactant that's getting used up. So I throw a negative sign on there as well. In the problem, it says this is rate of consumption. Right? Rate of consumption means negative value for the rate. Right? Consumption is telling us there's the negative value there. So that's how it is for compound A. And now once I have this rate of reaction relative to compound A, I can say, well, okay, how does the rate of reaction compare to compound B? Well, every time the reaction goes, only 1 mole of B is used. So I'd end up with just delta B, delta T, right? Except for it's also disappearing, so it's a minus. Sometimes I'll include a 1/1, so it's 1 reaction for every 1 mole of B, right? It's essentially like a mole ratio, a mole fraction, in a mole ratio in front of each component rate. That's the rate of A, that's the rate of reaction. That's the rate of B, that's the rate of reaction. And then I can do the same thing with the appearance of D, where I can say, look, the change in D with respect to time. Now D is going to appear 3 times faster than the reaction is going. So if I want to get D to be the same speed as the reaction, I need to cut it by 1/3. I'm just looking at the molar coefficient. That's where that 1/, coefficient idea comes from. And so now I can relate all 3 of these just to rate of reaction. Now, if I know the rate for A, can I plug that in and find the others?
No.
Yeah, we can. Right? I can pick these 2 things are equal to each other. I've got the number for that chunk, cut it in half, and that's going to be B. Sorry, not cut it in half. Oh yeah, cut it in half. Because they gave us the rate of A, not the rate of reaction. Cut the rate of A in half, and that will get you the rate of B. Consumption.
I feel like maybe this is related to something different that is on rates also. But I thought that the formula or whatever doesn't affect or it just doesn't affect the concentration values. Is that what it is? Or there's something where it was specifically asked us if the coefficient.
Oh, that's for the rate law.
Oh.
Right, the rate law.
Okay.
Right, so the rate of reaction.
That's different.
That's different, right? And the rate of reaction is, proportional.
Rate law is the written out, that's the K.
Yeah. So when we do rate law, here's the funny part. When we do rate law, this rate is still rate in, let's say we're doing K times concentration of A to the N, concentration of B to the M. This rate law, right, these 2 rates are the same thing. But this is the rate in terms of each component of the reaction. This is the rate law for the overall reaction.
And those 2 values would be different?
Well, the rate value would be the same, but how that rate relates to A versus B, right? This thing, each moment in time, this only works for a snapshot when we're looking at a delta A, delta T, where we have specific values for delta A, delta T. This thing works for us to kind of get to the integrated rate law, right? And figure out like what's going on. The other thing to keep in mind is this idea of how compound A is changing with respect to time, that has to be experimentally observed and measured. That's essentially the plots that we were making.
Yeah.
And if it's not a straight line, it's kind of a mess. So we were just doing initial rate laws. And when we're doing initial rate, this whole thing up here is great. But when we start looking at it over longer times, when we take the fact that the changing concentration changes the rate, we have to start looking at the rate law for it to make more sense, for it to be more experimentally useful.
And so when we use rate law, we don't take into account the formula.
Well, the formula does not directly impact the coefficients, the order of the reaction.
Okay.
But we can still, once we have the rate, we can, whether we get it from the rate law or from some other way, once we have the rate of reaction, we can relate it back to how much compound A is being used, how much compound B is being used, and how much compound D is being produced. The thing that the rate law is trying to get at, that makes it a little bit different than the differential rates, is as A is being used, how does the rate change? Right, so this is the rate, and this is where we have to look at, are we looking at instantaneous, initial, or average? Because we need to specify what type of rate we're looking at. This is the rate at any given concentration. If we know the concentration, I can tell you what the rate is, if I've got the rate law. So they're kind of getting at different information. And we really need both, all of that information for it to really be useful. Key terms definitions, lots of key terms definitions here. The key terms and definitions in this section are, they're as important as any time we've got key terms and definitions, but I would say they're more nuanced. They're more, you have to be a little bit more detail oriented because rate law, rate with respect to compound A, rate of reaction, right? They're all these things that sound the same, but they're all talking about these importantly different things inside of the concept. So let's go ahead and let's keep going with this. Let's just get the answer for compound, but you can take this chair if you'd like. Let's get the answer for at least how fast compound D would be appearing. So in this situation, we're going to take the 4.97 times 10 to the minus 4, and then we've got the negative already, right? Because consumption's a negative, the negative's a negative, so I'm going to divide that by 2. And that's going to get me the rate of reaction is 2.485 times 10 to the minus 4. If I want to get it in terms of D, I would have to multiply by 3. So I'm going to multiply by 3. And we're going to get 7.45 times 10 to the minus 4. The other way to think about what I just did is I just said, what's the mole ratio between A and D? It's a 3-to-2 ratio.
Would it be negative for D? Because since...
No, D is going to be produced. And I gotta throw my delta T's in there, right? So I took that 3 over there and multiplied it over here. This is the ratio. If we look at the unit analysis here, right, this is 3 moles of D for 2 moles of A, and this is a delta A.
How do you get rid of the negative though? For like, because if you like, because it's like saying that like the change, like delta D over delta T is equal to negative 3 over 2 delta A over delta T, right?
Yes.
At least like mathematically, or do you just like you just
Consumption is the negative, right? So this delta A delta T is actually a negative 4.97 times 10 to the minus 4 if we just think of it in terms of rate and not rate of consumption. And so that word of consumption essentially erases that negative sign. Because you're not talking about rate of reaction, you're talking about rate of consumption. So again, this is a problem we've seen before when we were looking at delta H's, and we said heat is released, and do we say essentially if delta H is negative, or do you say 300 kilojoules per mole released? Right, both of those are saying the same thing. One of them does it mathematically, one of them does it conceptually. But that 300 kilojoules per mole released, the word released is doing the negative sign.
Yeah.
Same thing is here with consumption. Consumption is doing the negative sign. Okay, that's number 3. Did you have a specific question?
Yeah, I was just wondering if you have any slots open in your Tuesday final section? Or the Thursday one?
Which section are you in now?
I'm in the one that has the final on Thursday, the Tuesday, Thursday, 3 to 6.
Which class is that?
Chem 127.
3 to 6 or 6 to 9?
3 to 6.
3 to 6. I have space in the 6 to 9 final.
Okay, and that's the one on Tuesday?
Who's in my 6? Yes.
Yeah.
I don't know unless I get the syllabus out.
Okay, can I just email you about that?
Yeah, email me about that.
Okay.
I've got space. I don't have space. Our class, our 3 to 6 class is like completely packed.
Yeah.
So if you were trying to do it that way, it wouldn't work. But my 6 to 9 has a couple open seats.
Okay,
So that should work.
I will
Just
email
email me, make sure I respond. If I don't respond by class tomorrow,
you.
ask me again.
Okay,
This
sounds
is a weird conversation to have on camera, but
Sorry.
it's fine.
Thank you.
No, it's okay. Are we ready to look at number 7? Always get written verification if an instructor agrees to something. Because I will forget that conversation just happened because I'm going to go do number 7 now, and I'm going to, it doesn't matter. Okay. Number 7, more questions about this?
Wait, so to get the D, is it not the same as just doing like 3/2 of the?
Nope, it's exactly the same. Right, that's what I'm showing down here. Is like if you got 3 molarity of D per 2 molarity of A times your delta change, your change in concentration of A, that's D, right? So it's rearranging these coefficients, right? The coefficients, the point in these like 1/2, -1/2, -1/1/3 is reaction per A, reaction per B, reaction per D. Right, so that's how we get it to rate of reaction.
I'm getting that's wrong. That's what like I just put it in.
Well, let's move on to the next
Yeah.
problem. If it is probably a negative sign or something else, and I can pause the video and we can troubleshoot whatever that is, or we can go on to number 7. Preference? I'll do either one.
Oh wait, no, it's just because actually I know why it's wrong. It's okay.
Okay.
Yeah.
Are you sure?
Yeah, it's because I put to the -4, but in here it's to the 4.
Oh, okay, yeah. Sorry, I misheard you, and so I did
No, that's
negative
okay.
4.
That's okay.
That would definitely make Lab Pal unhappy. Okay, let's move on to number 7, yeah?
Yeah.
Okay. 9.2, number 7. I don't know what it is, you have to tell me.
Right, sorry. Number 7 is, so it's the same reaction. 2A plus B goes to 3D. And then through the experiment, we determined that the rate of this reaction is first order with respect to A and second order with respect to D. To B, sorry.
I was going to say, whoa.
And then so write a rate law based on the experimental findings for this reaction. And then how will each change listed below affect the rate of this reaction?
So let's write the rate law first, and then we'll look at change. So if it's first with respect to A, second with respect to B, we're just going to have rate is equal to K times A times B squared. Okay.
And then, so it's saying, like, how will each change listed below affect the rate of this reaction?
Yeah.
So if you double the concentration of A, and then triple the concentration of B, half the concentration of B.
Oh, those are separate things. We're not doing that all at once. So if we double A,
Yeah.
what happens? If that gets twice as big, that gets?
Twice as big?
Yep.
Alright.
If we, what was the second one?
Tripling the concentration.
If we triple that one,
It's
gonna
9
be
times.
9 times? Yep. What's the next one?
Having B, so that would be
quarter speed, because it's a half squared, which is a quarter.
Okay.
That's it.
And then doubling both of them, that's just...
It's going to be 2 times 4, that's going to be 8 times increase.
Okay.
You good?
Yeah.
Okay. Any questions on that? So I guess my question is, where'd you get stuck on that one? Because it feels like it was pretty straightforward.
Yeah, I don't know. I think because I tried to do I was plugging in numbers to see what it would look like.
Okay.
But then.
So let me show you how I kind of do this. So we just did it pretty logically, right? And it worked out fine. So the thing I would do, and it's kind of like, how we had our experimental comparison thing we were doing? I would write it as kind of like A0 and B0 become 3 times A0 and B0. Whoa, that's not good. Let's write that up. Right, so this would be for that first one that says what happens when you triple the rate of A. Or maybe it was rate of B, right?
Oh, yeah, and then you can just tell where you switch.
Right, and then you can see you get a factor. You're going to get the same original rate law out, but with some extra factor on it.
Yeah.
And so that's how I look at it for when it says triple A, triple B. The problem with plugging numbers in is if you plug in a concentration of 1 for these, sometimes you can make their importance evaporate because 1 is tricky, and then if you start doing decimals or oh, let's use 2, you can run into weird mathematical quirks.
Yeah.
Where something happens that you don't expect. Because if you're doing 1, but that's the way
and then I think that.
You can run into some mathematical quirks, just coincidences essentially.
Yeah.
So this is the way I do it, where I think about what is A. What if I had 3 times that? And so I just plug in 3 times A in for my A. So I do this. 3x A naught is equal to A. And then I compare, how did it look originally? How's it look after?
Yeah.
And the nice thing about doing it this way is I can do it in my head pretty easily.
Yeah.
Yeah? Okay. Number 9.
Could we do 16 really quick?
Let's do 16 real quick. Yeah, let's do 16. Thank you for letting me know. Otherwise, I would have kept going. Let's look at number 16. What's number 16 say?
The generic reaction below is followed by the formation of D. 2A plus 3B goes to 2C plus D.
And we're tracking D to tell what's going on. Is that what it said? It said we're followed by the formation of D?
Yeah.
Okay.
And then it says when the initial concentration of A is much greater than the initial concentration of B, a plot of D versus time T.
Well, hold on.
Sorry.
Concentration of A is much greater than concentration of B.
Yeah, the plot of D versus time T is linear, or the concentration of D is linear.
Okay.
And then
Well, let's just analyze this first piece of information to start. What the heck is this trying to tell us? So, a couple hints come in. First off, obviously it's a rate law thing, right? It's a rate thing. These plots were rate law things, so it's a rate law thing. So let's just write down the rate law. The rate law is going to be K, A, B. Right? And then it's got this extra, why does he tell us this? The concentration of A is much greater than the concentration of B. This is one of the really important things I said in class. I was like, the book doesn't do this well. Make sure you write it down and take good notes for your classmates that aren't here.
Is it something about the N and the M? If you increase it a lot, then it won't. Or is it 0? It's a 0 rate reaction or whatever.
Something around those lines.
Okay.
Right? So what we're doing here is, if I said pseudo-order rate law, would that sound familiar? No.
Not to me, but yes to everyone.
I don't know.
Right, so essentially what we do is when we say A is much, much greater than B, right? I'm using a double greater than sign to be like, it's not just a little, it's not just greater, it's like way greater. That means, so like A has a value of like 1,000,000 and B has a value of 5. So when the reaction finishes, B goes to 0 and A goes to 999,995, which is still about 1,000,000. So in that situation, concentration of A is approximately constant. That means I can write a pseudo-order rate law of rate is equal to Ka, that's all constant, times B to the n. So I see that when I change the concentration, like, so when I do a plot and I track this, D, concentration of D versus time is a linear plot. Okay, linear plot, is that 0th order, 1st order, or 2nd order? Do you remember the 3 different plots and the 3 different things that give us order?
0 order?
This is 0 order. So the production of D should probably be a positive slope because we're tracking a product and not a reactant, so it should be appearing. But the concentration of D is, changing over time in a linear way. And we look at this and we say, oh, what does that tell me about changing the concentration of B?
Thank you.
Hey, you bet, see ya. Does changing the concentration, so read me the sentence again that we're analyzing.
When the initial concentration of A is much greater than the initial concentration of B, a plot of the concentration of D versus time T is linear.
Okay, so as time goes on, the rate of the reaction is not changing. So as B disappears, as the concentration of B changes, the rate does not.
Okay.
So 0th order
Is for B.
Yeah. How's your plot look?
I'm not sure right now.
Let me take a quick look. Okay, let's keep going with this because you also have to go. Okay, what's it say next?
When the initial concentration of B is much greater than the initial concentration of A, a plot of concentration of D versus time T is
Oh, that's boring.
linear.
So this problem is randomized and you just got the boring randomized one?
Yeah, so they're both 0.
Yeah.
Okay.
So that means our rate law, what's it ask next?
It's asking what's the appropriate rate law for this reaction.
Mine is like the natural log of D. Does that change it?
Yeah, it changes it. That's
How do you
part of
take
the,
into account
that's
the
part of
natural
the, so
log?
which one was natural log? Let's do this one as,
It's the same thing, just both of them are natural.
let's
log of D.
say this one was natural log just for fun. Right, so this one was natural log of D, was linear. What order does that suggest? 0, 1st, or 2nd?
Would it be first?
Yeah.
I just guessed because the half-life is natural log of 2 over K.
Right, well, so, oh, you got your equation sheet right there? Look at the integrated rate law, right?
It's also natural log of D.
It's natural log equals negative K. So these are the these are the linear forms. A naught is the 0th order. Natural log is 1st order. 1 over 2nd order. So this would be 1st order. Now, is this 1st order relating to compound B or compound A?
Would it be A?
It's A. So in this case, that tells us N is going to be equal to 1. So what we look at here, when B is much greater, we'd have essentially the opposite thing. Rate is equal to K times B, where that chunk there is a constant, times concentration of A to the N. And when we measure and plot, we can tell. So you can start to see how we can do some experimental control to figure out. So in our lab on Thursday, we were doing this initial rate measurement where we were just measuring the first few seconds, and we were doing 3 different experiments and taking ratios of the different experiments to figure out what the order of the different things were by doing careful design. We can do the same thing with these integrated rate laws, where we can decide which thing has high concentration, which thing has low concentration. The thing with low concentration that's going to be significantly changing will then impact the rate, and we can measure that in C and do 3 different plots to figure out what's going on. We're doing that tomorrow in class. We only need 1 set of data, but then we need to make 3 plots with that 1 set of data to figure out which one's most linear. A lot of students don't like it. But we'll have time in class to do data analysis like we did last time. Because I know this one has a lot of data analysis questions.
Is it similar to the lab we did on last Thursday?
Yes, the data collection is easier, but the data processing, the data analysis is a little harder.
Okay.
So that's number 16. Was there anything else we missed, or is that good?
No, that's good.
Okay. Right?
Thank you.
And so it really is this idea of, I showed you that one slide where I was like, this is everything you need to know about rate laws. That slide. Yeah, that's the big table.
Yeah.
There's even a homework question that most people don't do because there's nothing to click on that says, in your notes, make the table of everything. And I had a student who did it, and I was really surprised because it's not somebody who's been doing, well, they're doing better now, but they didn't do well at the beginning of the quarter. They changed their study habits. And they're like, oh yeah, I started doing all of those questions because they're really important. I'm like, I know, that's why they're there. But most people skip them because you can't click on something.
Mm-hmm.
Okay. Number 7? Yeah?
I think number 9.
Number 9, oh yeah. This is what I get for not crossing things out as I go. We did 3, we've done 16, we've done 7. Number 9.
This one is the reaction, lowercase a, uppercase a, goes to products. Is the first,
I think I know what this one is.
Yeah.
Let's see.
is a first order reaction with the rate constant.
Goes to
Products. Is a first order reaction with the rate constant of 1.084 times 10 to the
What was that?
negative 4.
1.084
times 10 to the negative 4 inverse seconds.
Yeah. See.
How long does
Thank
it take for the initial amount of A to decrease by 35%? And
Oh.
then how much remains after 25 minutes? What is the half? I know the half.
Okay.
And then
So
how,
we want to get
I was really confused. I wasn't sure
35%.
what to do. Because I thought, I was like, oh, what if I did but I was at Chem.
I'm going to show you.
tutoring.
It's the same. It's the same trick that we just did.
Oh, really?
For what happens if you double. So
Oh,
this is
okay.
first order, which means it's going to be natural log of A at time t is equal to negative kt plus natural log of A, 0. And I want to get to 35% of my original. How could I write 35% of my original? A naught.
1 minus 0.3. For 35% of it, 0.35 times it.
Plug that in and solve. That's it. Right? And you'll notice, if we leave it as 30.35 A naught, we get some really nice mathematical tricks that come in.
Like plug it into the
Right, now-
integrated rate law.
Yeah. Right, so watch what happens mathematically.
But I don't have an initial. I don't have a overall or a something n concentration.
Don't need it. This is the end concentration, right? 35% of A naught. The thing we don't have is what's our A naught. Do we want to set it to a random number like 1, 5, 10, 15, 20, 30, 2, 0.5, 0.2, 0.1? Sure, we could, but let's think about this mathematically first. I'm going to have natural log of 0.35 A naught. I'm going to leave the brackets off just because I'm feeling lazy. Minus natural log of A naught is equal to negative kt. Because of the rule of natural logs, I can turn this into the natural log of 0.35 A naught divided by A naught is equal to negative kt. Watch what happens. A naught cancels out. because it's first order, the initial concentration doesn't really matter because it's going to go faster or slower depending on if there's more concentration or less concentration. So to get to 35%, whether you've got a high concentration or a low concentration, takes the same amount of time. So it's just the natural log of 0.35 equals negative kT. This is also how the half-life works, right? If we want to do half-life, it'd be natural log of 0.5 equals negative kT, which is going to get us natural log of 2 equals k, or equals t. Natural log of 2 over k equals t. So that's how we do that first. That one I think is the most confusing of the four.
Yeah.
Right? Because people don't think about how they can rewrite the initial concentration. How do you write 35% of the initial concentration?
I was trying to.
0.35 of the initial. But once you see that, it's like, oh, that's it?
Yeah.
And it's like, yeah, that's it. Right? The same thing we saw. That's where I said it's the same trick. It's like, what's double? How do you double A? How do you do double the concentration of A? You just say you've got an A naught and then you've got 2 A naught. How does that affect? Right? We got some A naught. What if we had 0.35 A naught? Solve.
Okay.
What's the second one? So that's how we do the first one.
How much remains after 25 minutes? But I think
At 25 minutes, we've got the T. How does that specifically ask it? Let me see something.
enter as a percent without the percentage.
Okay, entering as a percent without the percentage is back to this. So if we, notice with that canceled out, I can re-erase this to just call this right? 0.35, 0.25, 0.5, like whatever our percent to remain is just going to be whatever number is inside that natural log.
Oh, so then we just plug in for t and then solve for the natural log of
Mhm.
blank. Okay.
So you're going to do e to the negative kt, and that's going to get you your percent. And again, it's one of those weird things, like this is one of the things that makes first order rate laws really nice, is because you can do everything in terms of percentage of original, because that original concentration just cancels out. We don't see that with the 0th order. We don't see that with second order. This is also part of why half-life even exists, because it's your 50% life, right? It's your percent remain life. And it makes a lot of sense for first order phenomena. Half-life does not make a lot of sense for 0th order or second order, in my opinion, which is part of why, it's, when I first learned about half-life and I was like, oh, it's just a time, it didn't make sense to me. And then when I learned about half-life with respect to 0th order rate law, I was like, this feels clunky and cumbersome, it doesn't feel useful. But when I learned about integrated rate laws, actually learned the definition of what half-life was, and was like, oh, for first order situations, the half-life is always the same value, which makes it a great way to characterize your speed of reaction. Essentially, half-life becomes another way to define your K value.
Because it's not dependent on concentration.
Because it's not dependent on concentration. So I spent probably 3 years completely confused about why half-life was a good idea. And it was like when I first learned about it in some high school class with carbon dating, where it's like, I don't understand this half-life thing, it seems silly. And then it was literally the end of my freshman year of college when I was learning rate laws that I was like, wait, is this related? And they were like, yeah, it's the same thing. And I was like, oh, this makes sense now. What was the third one?
The third one I know how to do. It's just what is the half-life. So
and the third one is a constant, right?
Yeah. And then
you don't need your original A for that. The original A cancels out because we can rewrite it like this.
Yeah. But then the fourth one, I think I know how to do it, but
Let's look at it.
How long does it take for the initial amount of reactant to decrease by 87.5? Is it just the same thing because there's only it just doesn't say A, but it's just saying it without saying A.
Okay, it also says it in a weird way, to decrease by 87.5%.
Yeah.
So our percent, the reason it's weird is because we've got this set up as percent remains. So we would have to do 100% minus 87.5% equals
But the first ones are the same thing.
12.5. You're right, 12.5. Oh, did we do the first one wrong?
What, the first one says, how long does it take for the initial amount of A to decrease by 35%?
By 35%, not to 35%. We did it wrong.
That's okay.
Right? This is
Just
to 35%, not by 35%. So that's an important distinction there, right? Sorry, this is where, again, key terms, vocabulary, reading differences. To 35%. By 35% would be 65?
Yeah.
Makes a big difference. So paying attention to those little vocabulary things is important.
So would the percent remain thing still be?
Yeah, so we did the percent remains.
Okay.
Right? So what I did it for percent remaining, not percent disappeared.
Mm-hmm.
It'd probably be useful if we recreated the equation to be in a percent disappeared like way, just because a lot of things we'll talk about it in terms of how much is left rather than how much is still there.
Mm-hmm. Would that just be like 1 minus that number?
Yeah. So you'd have 1 minus percent, well, you'd have
It'd
to
be like
do
1 minus x is equal to e to the power of negative kt, and then you just, you know.
Yeah, it'd be something like that.
So for part D, it's asking the same thing as part A, but it just doesn't say A, so that's why I was just like.
Yeah.
But the A is the only reactant.
It's the only reactant.
Okay.
Right, if there were 2 reactants, I'd have to specify which reactant it's talking about. But that also gets more complicated, and you'd have to probably do it in a pseudo-order way where one of them is constant. Because remember, all of our, all of the integrated rate laws we're dealing with this quarter are all either single reactant dependent or pseudo-order.
So would it tell us like, oh, this one is way bigger than this one, so that we could.
And that would be our big hint that it's doing pseudo-order.
Mm-hmm.
Is like, the reaction would be like A plus B, and when measured with concentration of B much greater than A, we find all this stuff. Right? It'd have to give us that little like hint that it's doing pseudo-order. That's all the questions on the list. Do we have other questions? I'm going to pause the video for now.